Okay. Ben Herzog and Yaniv Balmas are going to give you a very good overview, I've been told, about crypto failures. Please go ahead.
Hello. So my name is Yaniv, and with me here on stage is Ben. And we're here to talk to you today about great cryptographic failures. Now, as you all are probably aware of, cryptography has been really increased in the past few years in the malware scene. More malware is using cryptography, and more malware is using better cryptography. Now, this sometimes puts us as malware researchers or malware analysts in kind of an unpleasant position. We're expected to show abilities that were usually reserved to mathematicians, PhDs with mathematics or crypto analysts. And we're here to tell you today that this is usually not the case. You see, the bug usually is not in cryptography, but the bug is usually in the men implementing cryptography. Now, we've gathered up some examples that we've very fine-picked, and hopefully we can relay this message by those examples. And just a short disclaimer before we begin. If you find a cryptographic bug and you go ahead and publish it, then you'll probably get good PR, but I think, or we think, that you're actually doing the wrong thing, because all you're doing is giving the attackers, the malware authors, all the information they need in order to fix it, and then we kind of just lose our leverage, and that's not a good thing. So we are not going to show anything new here today. All the examples we're going to show have already been published or already been fixed, right? But it's not the examples themselves that are important, it's the takeaways. And without further ado, I will let Ben present the first examples.
Okay, thank you, Yaniv. So the first category of crypto failure that we're going to talk about is voodoo programming. Now, voodoo programming is programming that stems from a warm, fuzzy feeling in your gut that the code you're writing right now seems kind of like it could be the right thing to do, possibly. Now, some crypto failures completely wreck crypto systems, and we'll see some of those later. But some crypto failures, like the one that we're going to see right now, they don't do that much damage. What they do is give us a window into the troubled, paranoid soul of a malware developer, and the way that ultimately they have no idea what they're doing. So let's talk about Zeus. It's the granddaddy of all banking trojans, and it caused tens of millions of dollars in damages, but we're not here to talk about any of that. We're here to talk about the way that Zeus encrypts its outgoing traffic. To encrypt its outgoing traffic, Zeus uses something called RC4. It's a stream cipher invented during the 80s by Ron Rivest, and RC4 is very popular to use in malware for two reasons. The first reason is that it's very, very easy to implement. If you see that picture up there, half the RC4 logic is already in it. And the second reason RC4 is so popular to use in malware is that it's good enough. You may have heard about attacks on RC4 in specific situations and so forth and so on, but to encrypt outgoing malware traffic, RC4 should do. But the Zeus guys did not agree, and for Zeus, they decided to introduce their own brand new redesign of ARC4, which we like to call ZARC4. Now, if you look at ZARC4 and try to spot the differences, soon enough you'll realize that the only difference between ZARC4 used in Zeus and RC4 is those last two lines. What they do is that once you have your RC4 ciphertext, they take each byte from the ciphertext and XOR it with the next byte to produce a new improved ciphertext. Now, I've told this story by now to many people, and what they all had in common was their complete lack of a reaction to that last part, which is a pity. I mean, guys, if you take a crypto system, and to the end of that crypto system, you append a constant linear transformation, you have added zero security to that crypto system. None. It's like relaying your ciphertext in pig Latin, completely useless. So we're left with one question to ask ourselves, which is why? I mean, it's not even just the Zeus guys that do this. Out there is a veritable sea of malware doing this kind of thing, introducing modifications and tweaks to crypto that's been known to work. So we can't really read the minds of malware developers, but we have a working theory. So let's put ourselves in the shoes of the Zeus guys for a moment. They believe that out there's this shady guy who wakes up every morning thinking to himself, today I'm going to read me some Zeus traffic. Now, this guy has access to a magic box, and this magic box can stare RC4 ciphertext straight in the face and decrypt it, just like that, without having the key. Now, I can't do this. I'm willing to bet nobody in this room can do this, and probably this building, but this guy can. Now, the Zeus guys cannot bear to live with this threat. So, in their desperation, they resort to the only trick they can think of in this case, which is a Jedi mind trick. They extend their hand and say, Mr. Agent, this is not the algorithm you're looking for. Your magic box works on RC4, and we're using Zark4. You see, it's completely different. It has this linear transformation at the end. And they imagine that this guy is now going to slump his shoulder and go sit in the corner and cry. Actually, what's going to happen in this delusional paranoid fantasy is that this guy is going to take 5 minutes to see some reverse samples, some traffic captures, put 2 and 2 together, and then apply the inverse linear transformation, right, to the Zark4 ciphertext, and then run his magic box that we have assumed existed, and he has decrypted the ciphertext, and we're right back where we started. Actually, that's not quite right. We're not right back where we started, because earlier this guy had a problem. He needed to fish out Zeus traffic out from a sea of other RC4 encrypted traffic, which looks to him just like it. But now Zeus uses its own and unique encryption scheme, Zark4, and we've just shown that this guy is capable of decrypting it. So now all he has to do is easy peasily search the web using his Zark4 decryptor, which we have just proven exists. And he'll be able to automatically fish out all the Zeus traffic he wants. So even if we accept this delusional paranoid scenario, what we find out is that the Zeus guys try to disguise their outgoing traffic, but in the end, all they managed to do was to draw more attention to it. So the next example we're going to talk about is Linux Encoder. Linux Encoder is the first reported ransomware for Linux, initially discovered late 2015, and it propagates mainly via vulnerability that was discovered at checkpoint. So here's a link in case you care about that. Now, on the face of it, Linux Encoder knows how to encrypt. It uses AES encryption. It uses the CBC mode of operation, so you cannot see the penguin. And it uses third-party open source crypto libraries. So the chances for strange homebrew crypto bugs are reduced here. Now, much like other ransomware of its kind, when Linux Encoder wants to encrypt a file, a victim file, it generates a session key in order to perform the encryption. And in order to randomly generate a session key, you need a source of randomness. Now, if you're on Linux and you need a random value, usually you would use dev random or dev random, but those guys came into it in a very Windows frame of mind, so they decided to use the current timestamp as a source of randomness. Now, even if you're on Windows, that's not the best way to do it, but those guys said to themselves, what the hell, it's probably going to work, right? And if you look at the Linux Encoder executable, you'll see that one of the first things that happens is that it extracts a seed, a random seed based on the current timestamp, and then all the rest is pseudo-randomly generated from that, including all the session keys. So let's recap what we just did. We took the current timestamp, we used it to generate a session key, we used the session key in order to encrypt a file, we took the encrypted file and we wrote it to disk. So far, so good, right? Where's the catch? Let's think about this again. We just created a new file. This file has new encrypted content, and another new thing it has is a new timestamp. Do you see where this is going? Okay, well, here's a chart to help you. Do you see it now? Now, what's going to happen? Right? The user, the victim, now has access to the newly created file, which has a new timestamp, which is suspiciously like the old timestamp, which can be used to generate the session key, which can be used to decrypt the file. Now, this is like the villain in the movie Taken, contacting Liam Neeson and saying to him, "We have your daughter. I will never tell you where she is, but you should know that 2 seconds ago she was in the hotel lobby." I don't know, completely ridiculous. Now, the crypto community, of course, could not just stand by idly and let this excellent design choice pass by without comment. Feast your eyes on this. The Grok's completely useless advice here, right? You won't get any extra security by running a hash function on the time. But you know, the Linux Encoder guys, they took one look at this, and with sparking eyes, they said, yes, that's what we need in order to improve our ransomware, more hashing. And soon enough, a new and improved version of Linux Encoder came out, which takes the seed and generates a session key from it by running a hash function on it 8 times in succession. 8. Of course, as we all know, that's 8 times as secure as running the hash function on it just once. Now, to be completely fair to the Linux encoder guys, they did fix their original problem, and they made sure that now the new encrypted files will not have the old timestamps, will have the old timestamps instead of the timestamp that was used in order to generate the key, or something close to it at any rate. And so the old attack did not work anymore, and this would have been the end of it, except for a small hiccup. You see, the Linux encoder guys, they forgot to tell Polar SSL what hash function it should actually use. So it kind of shrugged and said, what? Okay, I guess then you don't want me to use any hash function. So all the 8 calls to the hashing logic don't actually do anything. And the seed that's appended to the end of every victim file for verification purposes is actually equal to the AES key that's needed in order to decrypt the file. So apart from that small technical issue, the ransomware was in excellent condition from that point on, and all is well that ends well. So what are our takeaways from those 2 examples? First of all, if your encryption is not broken, don't fix it. Second of all, if you're up against encryption that's using the current time in order to draw some of its randomness and power, follow the timestamps. You might find something interesting. And third of all, and most importantly, don't listen to the grok, because it's probably trying to troll you. Now, the next category of example that we're going to look at is what we like to call the copy and paste problem. Now, I'm sure nobody in this room has ever copied and pasted code, but I hear something common. People sometimes do it. And one example of people doing it is the crypto defense ransomware. Surfaced around 2014. It's a clone of CryptoWall. If you look at the ransom node for crypto defense and the one for CryptoWall, you'll barely be able to notice a difference. I barely can. Now, crypto defense knows on the face of it how to perform encryption. Again, it uses public key encryption, the RSA 2048 algorithm. And the way it works is that once an infected machine gets hit, it generates 2 keys, a private key and a public key. The public key is used to encrypt the victim files. The private key is then sent over to the CNC server. And now only the CNC server can perform decryption. Well, actually, if you're writing ransomware, what you should do is generate the keys on the server side. So we rate this design for ransomware 2 stars out of 5. But that's not such a big issue, actually, because I've seen ransomware make good money that I would have rated 0 stars out of 5. Right? It's not the best design what we have here, but it's a working design. And in order to make this working design a reality, the crypto defense guys needed access to a working implementation of RSA. Now, if you want a working implementation of RSA, the easiest way to do it is to use the Windows native cryptographic API. Or you could use a third-party wrapper library, but they decided to directly use the native API. Why? Maybe because it's less bloated, maybe because it draws less attention, maybe just because all the cool kids are doing it. But anyway, if you want to perform encryption using the native cryptographic API, you'll need to be familiar with those 3 functions. The first of which is crypt acquire context, which you will need to call because, of course, this is Windows and you can't do anything without acquiring a context first. Now, if we want to invoke this function properly, we'll need to do one of my favorite things in the whole wide world, which is look at the MSDN documentation. Now, this is all fascinating stuff, but excuse me if I'll hop over to the function prototype. Now, the first 4 parameters, they're pretty easy to figure out what should go into each one of them, but the last parameter is the flags parameter. Okay, now, hands up, everybody in here who knows point blank to tell me what should go in the flags parameter here. Well, no hands. Okay, well, I don't know either, which is why we scroll down to the documentation of the flags parameter. This is, mind you, the documentation for one flag, and not all of the flags parameter. And if we skim it closely, we'll see, first of all, 2 things. First of all, the flags parameter should usually be 0. But on the other hand, the crypt verify context flag should usually be set, which means that this flag should usually be set to both 0 and not 0. Now, I'm a reverse engineer and not a quantum physicist, so I really don't know what I should do with this information. And at this point, I'm really dazed and confused. So I scroll down some more, and by golly, I hit the jackpot. It's a code snippet with a fully formed code to crypt acquire context that just works. And what's the flag value? It's 0. It's just a 0. Our confusion is over, and so is the confusion of the crypto defense guys. Because you see, they went through the exact same mental process that we did just now. How do we know this? Because this same exact code from the MSDN documentation appears verbatim in their executable. Right? I personally pulled this out using IDA Pro. It's just there. It's sitting there word for word. And you see the flag is 0 again. Now, On the face of it, problem solved, but you know, I'm starting to get second thoughts and pangs of regret. I mean, we skipped so much documentation. Let's scroll back a bit to the documentation for the crypt verify context flag. And if we do this, we'll see that what does this say? When this flag is set, temporary public-private key pairs can be created, but they are not persisted. Now, we did not set the flag, we set it to 0. So let us take the contrapositive of this statement. Now, when this flag is not set, temporary public-private key pairs can be created, and they are persisted. Okay, what does this mean in plain English? It means that the super secret key that we generated in order to keep away from the victim so that they will never ever be able to find it, that they'll have to pay us good money in order to get it back, a copy of this key is saved in the temporary, in the persistent key storage somewhere under their application data folder. I guess that's not exactly what they had in mind when they wrote this ransomware. So what are our takeaways from this example? First of all, a less intuitive API is difficult to reverse engineer, but it was also difficult to work with. So the effort is greater in order to figure out what the person who wrote the code was trying to do, but the rewards may be also greater because the person who was working with it was more likely to make juicy mistakes. And second of all, if you got hit by ransomware, go check your temporary key storage, because who knows, this might be your lucky day after all. So without even further ado, I'm going to hand this baton back to Yaniv.
Thanks, Ben. So, next category, reinventing the square wheel. Well, I guess this needs no further explanation, kind of self-explanatory. So let's jump right ahead to our first example. You are all probably aware of the Petya ransomware, right? It was very popular in the beginning of 2016, and that is because it was actually the first ransomware to ever encrypt the MBR. So MBR stands for Master Boot Record, right? And that means that this ransomware did not only take your files as hostage, but it actually took your entire operating system as hostage. And if you've been infected, then after you rebooted your computer, you are presented with this very scary red skull ransom note demanding you to pay the Bitcoin on another computer, of course, because yours is completely unusable now. But yeah, that's the case. And now we were sitting there and thinking, how can we categorize those guys? Who are those guys behind the Petya ransomware? We've actually given this, I think, a bit too much thought, but then finally it hit us. We know who are those guys. You see, those guys are nothing but malware hipsters. That's what they are. I mean, they like doing stuff in the unusual way. Look at the MBR encryption, for example. I mean, we can argue whether or not it was good or it was bad, but what we can't argue about is that this thing was innovative. It was their own. It was the first time ever seen, right? And the encryption algorithm was no different. I can imagine those guys sitting at a table and saying to themselves, you know, we're not going to use any of this common encryption algorithm, any of these capitalistic encryption algorithms. We're going to use something of our own, something unique, something piquant, right? And since piquant was where they were aiming for, there was only one choice for an encryption algorithm, which is the Salsa 20 encryption algorithm. Now, if you haven't heard of it, it's okay, because as I said, it's a pretty hipsterish algorithm, but it's a stream cipher, symmetric stream cipher, and as such, it needs to produce a key stream. And the way to do it, in a nutshell, it has this struct over here, and this struct has these parameters to it. There's a sigma, there's an IV, there is a 16-4-bit stream position, and most importantly, there are 2 chunks of 16 bytes of password, right? Now, this entire struct goes into this very nice mathematical diagram that's pretty easy to implement, and the product of this is the key stream. That's basically it. So now, there is one problem that we're facing now, and this problem is actually a pretty hard problem. It's a problem humanity has been facing for many years, and there doesn't seem to be a solution for that. And that problem is, of course, determining how spicy your salsa is, right? How can you know it? So we like to tackle big problems like this, and we've actually put some of our best engineers to tackle this entire, this specific problem, and we are now proud to present for the very first time our brand new salsa ometer, right? So this thing can sense exactly how spicy your salsa is, and this of course includes our Salsa 20 implementation. As you can see at the moment, this is like the hottest pepper in the world. Something you wouldn't want to get near to without any chemical protections or stuff like that. And let's see how the Petya authors helped us reduce this spiciness of this algorithm, right? So first problem. If you remember, I talked to you about a 64-bit stream position. The Petya authors decided to save this in a uint32, right? So that practically means that the 4 high bytes will be constantly 0 and completely irrelevant to the entire keystream generation process, right? Yeah, way to go, Petya guys. The salsa ometer, of course, says that this is now no longer this red hot pepper, but it's another pepper. It's pretty hot still, right? But the Petya guys don't stop there, of course, and they produce this failure. And what I didn't tell you is that the Salsa 20 is based on something called an add rotate XOR PRNG. So rotate left is one of the main functions used in the entire algorithm, right? And what you see on your left is the C implementation of rotate left, and in the red box is the Petya implementation. And another thing I didn't mention is that MBR is, of course, a 16-bit architecture. So they had to shift everything from 32 bits to 16 bits, and they did this with the arguments, of course, but they very conveniently, for us at least, forgot to do it with the constants, right? So what you see here on the red box is no longer rotate left. It's something, I don't know, maybe like a shift left, not even that. Anyway, our salsa meter says that this is no longer this red hot pepper, but now it's like green pepper, still hot, but definitely not as hot as before, right? And fortunately for us, the Petya guys just don't stop. And they produce this failure, and this we called it salsa S20 hash. This is the actual core function of the entire algorithm. This is the function responsible of taking the struct and producing the keystream. And there's a very serious bug hidden in here. Can anybody spot it from just looking at that? Yeah. Let me give you a clue. Can anybody spot it now? Whoa. So again, as I said, 32 to 16-bit shift. So what the function is meant to do is to process 4 bytes at a time and then jump ahead 4 bytes in order to process the next 4 bytes, right? And what the Petya authors did is process 2 bytes and then jump 4 bytes ahead, right? So what this means for the algorithm is that, of course, that every other 2 bytes will be completely unchanged and again, irrelevant to the entire keystream generation process. So by this single mistake, they managed to reduce the complexity of this algorithm by half, right? And our salsa meter, of course, says that this is no longer this green pepper, but now it's, I don't know, it's not even a pepper, it's something like a Tabasco sauce, right? But still the hot kind of Tabasco sauce. And why am I saying that? Because, look, if we want to brute force this thing, the password, right? So first, let's get rid of all the irrelevant bytes here. And if you remember from the bytes left here, some of them are constant values. And if we want to brute force the password, they are, again, irrelevant. And then we are just left with 16 password bytes. Now, brute forcing 16 bytes is still not a practical thing to do, right? Luckily for us, Petya guys come to the rescue, and they produce this function. And this function is not even part of the Salsa 20 implementation. I have no idea why it's there. But what it does, it's called key expand. It's used to represent each password byte with 2 bytes instead of 1. So this means that instead of brute forcing 16 bytes, now we only need to brute force 8 bytes. And if you remember that the user has to enter this password through his keyboard, then you understand that these are not only 8 bytes, but they are 8 printable characters, right? At which point, our salsa meter suffered from a sudden crash. We're actually still investigating this crash, but the current speculation is that this thing is no longer a salsa, but it's some kind of a cucumber salad or something. This was, of course, broken shortly after this was discovered. So what are the takeaways? Argument types are kind of important, right? And whenever a programmer needs to shift from one architecture to another, from 64 to 32, from 32 to 16, then the place to go and look for bugs would be either the argument and variable types or the constant values. At least that will be the first place I would go look for them. And that's it for this example. And now our last example, which is not a ransomware at all, it's the nuclear exploit kit. You've probably heard of it, been very active between 2011 and 2016, and actually its operation completely ceased following our very nice, I think, publication of it. You can go ahead and read a bit if you didn't read it before. And now, when talking about exploit kits, the ecosystem is very complex, right? And it's very complex for a very good reason, because everybody is trying to catch those guys, right? And they have to keep it complex. But we're not interested in this entire ecosystem. What we're interested in is the abstraction of communication between the victim and the nuclear panel, right? Which looks something like this. There's an HTTP request being sent, and then the victim is served with an obfuscated exploit, and then a key must be shared between the nuclear panel and the victim in order to deobfuscate this exploit. The vulnerability is triggered, and you know what happens next, right? And what they did in order to share this key is they used the Diffie-Hellman key exchange, which you must agree is a pretty smart thing to do, right? I was pretty impressed, but let's look at how they did it. So, first of all, if you don't know Diffie-Hellman, I'm not going to tell you how it works, but just know that this is Alice, this is Bob, nice to meet you. It's an unsecured channel between them, and they do something that looks like this, right? And at the end of this entire procedure, you get a shared key. That's pretty much it for Diffie-Hellman. Good. Anyway, this can be represented by this very nice mathematical formula that has to be calculated on the server side. That's basically it for Diffie-Hellman. Now, this is how the Petya authors implemented this thing. And as you see, they just calculated this exact formula that I just showed you before, right? And if you notice, there's this function here, the getGMP function, that all it does is basically just base64 decode the parameters passed to it by the victim, right? So what can go wrong? These are the parameters being sent from the victim to the nuclear panel. They are JSON format. And can you see anything wrong here? Well, okay. So what's wrong here is that these parameters, they are not base64 encoded. They're just X values. Whoopsie. So what does this mean for our implementation? For their implementation. So if you look at the getGMP function, so what happens if base64 decode receives something that is not base64 encoded? Well, it simply returns false, which is, in our world, 0, right? And what happens next? If you look at these functions, so the GMP values get 0, making the P a 0. The A gets a 0 value, making the A a 0. So 0 to the power of B modulo 0, which just so happens to be the exact equivalent of the entire efficiency of this entire key exchange, which is, yeah, you guessed it, 0. So way to go, nuclear guys. Very nice code. So now, just to summarize everything with one sentence, if you consider cryptography to be a magic black box, then either you don't understand cryptography or it doesn't understand you. These are some thanks and credits for other guys doing research on the same subjects. And thank you very much. Any questions?
Yeah, we have about 2 minutes left for 1 or 2 questions. Crypto related, of course. Anybody?
Everything is clear.
Exactly. So let's thank together Ben and Yaniv.